I'm going to present then my work that is about extending the lifetime of NAND flash memory. So the lifetime endurance, the lifetime of flash is a known problem, a concern for many people, and we wanted to have a look a little bit more into it. So we took a flash block and programmed continuously its pages, and reported and monitored the bit error rate with respect to the writes, to the number of writes or program erase cycles for flash memory. So on the figure, we can see how there is a big variance in the degradation speed for each page. And what happens is that generally, in practice, when the weakest page becomes unreliable and the FTL detects it, I mean the flash controller detects it, it will flag the corresponding block as bad, but even if there are many pages that could still be that's it. Sorry, thanks. Could be written many times. So the question is, can we address this variance? So before going on, I want to give you some basics on NAND flash. So it's working on electron tunneling effects to remove and put charges into or from floating gates. So adding charges is called programming, and it's performed on the page level. Removing charges is called erasing, and it's performed in a coarser granularity on blocks. And as we cannot reprogram a page before erasing it, it enforces out-of-place update. Let me show you some example there. For example, we want to update the value of D4, so we are not reprogramming it on site. We program its new value on block D. And we continue to write in block D some new values. At some point, we will be wanting to reclaim some of the invalid pages that are accumulating. So we will trigger what we call the garbage collection. It will select a victim, so preferably with the least valid pages as possible, copy any remaining valid page, and safely erase it afterwards. And then we can proceed to program more and more pages. So for this work, we wanted to introduce a new state that will target the weak pages that we could detect there, for example. So this new state is called the relief state, which consists in bypassing those pages by not programming them. So we simply skip them and move on to the next page. Okay, so what we did with first was to try to characterize this effect. So we took 2 NAND flash chips from different manufacturers, and we weighed out a set of blocks. So we have first a set of reference blocks, which are used normally, which correspond to the red curve that you have there on the left. And we have 3 different set of blocks with relief pages at different rates. So 25, 50%, or 70% of relief rates. And you can see how the endurance is extended correspondingly. So it's important to notice that the endurance is not equal to the lifetime, or what we call lifetime here. The endurance is the total program erase cycles we can perform on a page or a block before it wears out, whereas the lifetime is the total amount of data, useful data we could write during its lifetime, during the life of the block before it gets unreliable. So we can use page relief to perform wear and leveling to reduce stress on specific pages. There is another aspect that is specific to multi-level cell that we will use. So first a little bit, some basics about multi-level cells. So they store 2 bits, and what is interesting is that each of their bits is mapped on a different page that we'll generally identify as LSB and MSB page, and they form a pair. So here I have a little illustration on the bottom, illustration of the voltage threshold of voltage threshold cell distribution. So at first, when the block is erased, every cell voltage is on the left at the erase state, and when the LSB gets programmed, we see that there is a single voltage threshold that is programmed. This programming is very fast because it's very coarse. It doesn't require a very narrow distribution. And then eventually we get to program the MSB, the second page, which target 3 different voltage levels and which requires to be narrower, and it's more requires more precision and is slower. So programming exclusively the LSB and bypassing the MSB, we could have an intermediate relief type. And it's equivalent to what we know, what we sometimes call the SLC mode, that is writing a single bit per cell. It provides 3 to 4 times faster writes than a program than MSB. And so it trade-offs capacity for better performance. So we have then 2 types of relief, the full relief, which is bypassing 2 pages, and the half relief, which is bypassing only the MSB. So now we move back to the characterization. So we had before what correspond to the full relief now, and we introduced the half relief. So we have now, we see an intermediate relief. So now how do they compare actually? So out of this data, we can extract the relative wear that is performed during a relief cycle compared to a regular program array cycle. So in this table, I report the numbers. So for example, for chip 1, the full relief will damage 39%. I mean, will provoke a 39% damage compared to regular program array cycle, and 61 for the half relief. But for the half relief, we write 1 bit, whereas for the full, we don't write anything. So when we compare the relief or the effectiveness in terms of written bits per cycle, the half relief gets more effective. So here in the example in the table, we have we've wrote, for example, 2 bits in 2 cycles. There are 2 ways to do that. Either we write once a regular cycle and then followed by a full relief, or twice a half relief. And if we sum up the relative or the recording corresponding wear, relative wear, we see that the 2 half relief is more efficient. So now we have a set of tools, but how to use them? So we need to look into the flash translation layer, which typically is placed between the file system and the flash memory, and hides all the physical aspects of the flash, and maps all the logical space into physical pages of the flash. So the mapping is not arbitrary. Otherwise, if it was randomly mapped, we will end up with many blocks with few invalid pages, and there will not be any good candidate for garbage collection. So what is generally done is we identify which data is likely to be updated soon, and we group all this data, this hot data, together so that we end up more frequently with completely or almost completely invalid blocks. And then reclaiming that those blocks will be cheaper. So those hot blocks are perfect candidates for the relief mechanism because they represent a small portion of the capacity and they are written very frequently, which increase the opportunities we have to relieve pages. And furthermore, with typical well-leveling techniques, we are sure that eventually every block is going to have its share of hot data, so relief opportunities by swapping hot and cold blocks. So now we know where to use our tools, but how can we identify those weak pages? So we will propose 2 strategies that we try to keep as simple as possible. So the first one that is quite intuitive is called the reactive strategy. We will identify weak pages on the fly. So let's assume the degradation speed of each pages, as we have seen in the beginning, slightly simplified. We assume some error threshold limit, where after that the data or the pages will become unreliable. And we introduce an intermediate threshold. And this intermediate threshold will tell us which pages are likely to be the weakest. So the first one that go through this threshold is likely to be weak. So every time this page that is flagged as weak is programmed in a hot block, we will relieve it. and we will end up with some block endurance extension. So we can, so for the first pages that get flagged, we can use the full relief because we need really to aggressively reduce their, the wear that is applied to them. Whereas for the last one, we have less, they have less time, I mean, they need less relief, so we could use the half relief for more efficiency. Now if we have a look at the overhead, in terms of storage in the flash, it would require 2 bits per page to store the state. Is it relief, fully relief, half relief, or not relief at all? So this will fit easily in the spare bytes that store the meta information. In terms of memory, we will need to do some bookkeeping. So every time a page is erased, we will need to remember what was this state. So for each block that has some clean pages, we will have up to 32 bytes to keep in memory. Oops, sorry. Yeah. In terms of performance, we need to frequently monitor the error level of our pages. So at worst, we will have to do an extra read for every program we perform, which corresponds approximately to 10% write overhead. So of course, we can leverage this by sampling a little bit this monitoring, not doing it every time, and also doing it on the background. And lastly, the capacity reduction in the block will necessarily increase the garbage collection frequency. So it's quite simple, but it's slow to react. It doesn't start to relieve the pages since the beginning. It needs to wait to identify them. So there is less potential. So we propose a second strategy. So that is based on an observation we made during our analysis that there is a strong correlation between the page number or position and its endurance. And this was also observed in some previous works. So based on this data that we have in advance, we can plan how frequently each page should be relieved to extend the endurance of the block. So for example, if we identified the weakest page in advance and evaluate how far we could extend its endurance, we could align all the pages that remain here on the figure on the left so that they match this endurance here. And we have an efficient block endurance extension here. The problem is that we do not know in advance how frequently we will get to relieve this weakest page. So what we propose as an alternative is to speculate on the number of relief cycle. So we first have a guess, or let's say we speculate on the number of relief cycle, for example 4,000, let's say, and we align the other pages accordingly. So this is what we would expect to see if we get 4,000 relief cycle during the lifetime of the block. But if at some point we exceed this total relief cycle, we'll need to evaluate to a higher one. Because if we don't do so and continue to use the relief rate that we set before, we will end up with something that is less precise and less efficient. So we need to recompute the relief rates for all the remaining pages in order to align them to the new endurance extension of this weakest page. In terms of implementation, it consists simply in lookup tables. So what happens is that, so we build these lookup tables based on the analysis that we did in advance. We have here on page 3, we have the weakest page that is fully relief. We can see 100% under the column full relief. And for other pages, we have some intermediate relief, so which will provide a good balance between half relief and full relief to get the best efficiency as possible. And this plan will be valid for 4,000 relief cycle. As soon as the block exceeds this amount of relief cycle, it will move on a second plan. So every time a block or a page is programmed while being on a hot block, it will have to look into the lookup table here, flip a coin, and decide whether or not it should be relieved. In terms of overhead, all the computational effort are done offline, so prior to this. It's not on the FTL or the flash controller. And in terms of storage and memory overhead, we need a 16-bit counter per block, which is identical actually to the, or similar, let's say, to storing the total program array cycle of each block. And we also need some extra storage to store the LUTs, which is typically about 1 or 2 kilobytes. And those LUTs are pretty sparse, so they could be easily compressed for memory-sensitive applications. In terms of performance overhead, as for the reactive approach, we have the capacity reduction of the hard partition that will necessarily increase the garbage collection frequency. So now let's look at the lifetime extension we can get out of it. So we start first with a simple model, not looking into a full simulation, but simply assuming constant write to some blocks. We characterize the endurance of 100 blocks, programming them normally. And in this figure, we show the lifetime, or let's say the endurance of each blocks, and they are ordered from the lowest endurance to the highest one. So imagining an application where we have a perfect well leveling, and assuming a maximum 10% of bad blocks before the device is considered dead. The dark gray region here will, correspond to the exploited block lifetime. And this is the perfect place where to compare with or to show some related work that were done that are closely related to what we do. On the left, we have salvaging bad blocks, which propose to reuse the valid pages, or the pages that are not completely worn out of bad blocks. And on the right, we will have a bare leveling. So we perform some bare leveling based on the bit error rate of every block. So ideally, every block will be used to its fullest endurance. So we will get, for this particular chip, plus 11% extra lifetime. Now, if we look at what we can get with the reactive approach and the proactive approach, it goes between 30% and 50% improvement. So this is for chip number 2, which has a quite large variance. This is the data you've seen on the first slide. I mean, corresponding to the first slide. But if we look at the first chip, we see some more disappointing results. There is in effect much less variance. There is much less room to improve anything, and this can be explained mainly by the difference in the architecture. So on the left, the chip 1 used an all-bit line architecture, which provokes less interference between the cells and is more reliable, and trades off some flexibility and area for that. Whereas for chip 2, which would be faster, will have less lifetime. So in summary, this shows that relief can fix large variances. But now, what about the garbage collection overhead that are not evaluated here in this simple model? So to evaluate them, we implemented 2 hybrid FTLs, namely rows and combo FTL, which a particularity is to map different regions of the flash with different granularities. So they have a buffer mapped on the page level and data on a coarser mapping level, typically block levels. And obviously for the relief, we will use the hot partition, which corresponds to the buffer. So this is the result. We run our simulator on a large set of benchmarks, the old TP financial applications, the Microsoft Research Cambridge traces, and we selected the traces with a significant amount of writes, more than about 2 gigabytes. And we also did our own, we collected our own traces from a tiny home server that ran for a week with standard services like web or mail, etc. And on the far right, you have the geomean for each of those measurements. So those are the results for chip number 1. The results are quite humble there because we don't have much room for improvement. And we get +6 and +3% lifetime out of this. For the second chip, we have most of the time more than 50% extension, except for a few cases. And so in average, we get 44% for combo FTL and 48% for rows. So now let's look at the effect on the performance. So as I said earlier, those two strategies will reduce the hot buffer capacity and increase the garbage collection frequency. But on the same time, we are using the half relief, which is corresponding to this SLC mode that has better performance. So despite the capacity loss, and thanks to the half relief, the execution time stays quite stable, and most of the benchmark actually reports even better performances. So actually lower execution time. So you should read the graph with the lower is the better, because on the y-axis we have the normalized execution time for each benchmark. And on the average, so for the first chip, we have -4% of execution time for combo FTL and -1.5 for rows. For the second chip, we have two cases where combo FTL behaves very poorly. It cannot identify efficiently the hot data, and will perform many garbage collection. This will provoke a large garbage collection overhead. But still, on average, we'll still get something like -1%, a marginal -1% improvement. So in conclusion, we characterized the relief effect. We showed that it was significant. The fact this potential varies widely, depends largely on the page level endurance variance. We proposed two simple strategies that could be integrated into FTLs. It can be implemented today with off-the-shelf chips, as we actually did. And we think that there is room to develop more efficient algorithm. As I said earlier, the computational effort were generally left out of the FTL, or we left the strategy very simple to implement, but we believe that for system with more powerful processor controller, we could do better at guessing what would be the hot-write ratio. And we also believe that technology scaling will inevitably bring a larger variance, and that relieving pages might help to overcome the challenge. Thank you.
Hi, my name is Ali Reza Haqdous from University of Minnesota. Thanks for your nice presentation. I think your approach works on page-level mapping FTL. Do you have any comment about any other like block-level mapping FTL, whether your idea works?
Right, so for exclusively block-level mapping, relieving pages will be quite impractical, because in block-level mapping you will be necessarily using the whole block. Here we are skipping some pages, so we would have to write them somewhere else. So that will be quite impractical. For page-level mapping, we actually didn't evaluate the result from page-level mapping simply because it takes much more time to warm it up and to see the effects of garbage collection. So we chose here the hybrid because it saturates away. So warming up, it's very fast.
Thank you.
Thank you.
So I have one question.
Yep.
The page skipping, did you notice any degradation in the data retention time, or did you measure that? Because when you skip the programming of subsequent pages, you can miss the trim that comes after to avoid.
On the relief pages?
Yeah. Well, actually, on probably the pages adjacent to the relief pages, you would see the.
I'm sorry?
On the pages that you program just before the relieved pages, you might see.
So the one on the next to them.
Yeah.
So what we have seen is a tiny degradation indeed, like at most 2%. But as they are generally stronger, it has no effect on the final balance of endurance.
All right, let's thank our speaker once more.
Thank you.